So, passive scalar turbulence, okay. This is one of the important topics. Yeah, okay. Things of water. So, we will end soon, okay. I mean, I am not going to get too long, but after this just summary and we will end by 6:20 or something. Okay. So, we covered hydrodynamic turbulence in the past, but there are always some secondary fields along with the velocity field. So, could be pollution, right, which is advected by the velocity field, or could be some chemicals which are uh, mixed by the velocity field. So, they come under scalar. So, this is scalar thing, okay. So, velocity field plus a scalar, could be temperature, could be particle density, okay, or it could also be magnetic field. So, then we have velocity field and magnetic field, or it could be velocity field and a polymer, okay. So, the secondary field can be complicated. So, I will just do one example, simple one with a passive scalar. So, this is a quite a important word. So, what does passive scalar mean? So, we write down the equation. So, I will write down the equation in the next slide. So, first is the equation of the velocity field, everybody is familiar with that, no. So, pressure gradient, Euro grad U, and this forcing for the velocity field is a large scale forcing, you can think of some stirring, and this is the equation for the scalar. Theta could be particle density, ink concentration in a water, or okay, and this kappa is the diffusion coefficient for the scalar, okay, which is same dimension as nu, which is L squared by T, velocity times length, and F theta is a forcing to theta, which is only function of, okay, it can be function of u as well, okay, but so theta is driven by u, right. Theta is this scalar is advected by the velocity field, at least here, or it could also affect F theta velocity field, but does theta respond, does theta affect u? So, you can see I do not see any u, I mean, okay, of course Fu may have some theta, but I say, well, Fu is not allowed to have any theta component. So, Fu is not a function of theta. So, this is not affected by theta. So, velocity field is not affected by theta, that is why it is called passive, okay. So, my theta is a passive scalar field. Now, you might have heard this active fields nowadays, no? There are a lot of people are on active field. So, what is active? If theta reacts on this, it is possible, for example, buoyancy. So, temperature affects the velocity field, then theta is a active scalar, okay. So, so we are not going to work with active scalar, which is more complicated. I am just going to tell you about passive scalar. Now, if this is not affected by the velocity Fi temperature or theta, then the properties is exactly same as what we did before. If you assume the Fu active only at large scale, then you get Kolmogorov spectrum, right. So, I did not need to touch, well, I can just use the results of the earlier lectures, no need to do any work, done. Now, I need to worry about this, okay. So, there are two objectives, one is does kappa get renormalized, okay, or and what is the flux, what is the flux for theta, the two objectives, or I will have some spectrum for theta, theta mod k squared, this is in fact this divided by k will give me E theta of k, this is spectrum of k, right. I mean, the way we define for velocity field, what is velocity spectrum, it is mod this squared by k, it is EU of k, right. So, I have this one. Now, there can be some proportionality constant, like Kolmogorov constant was there, similarly there is a constant for E theta, okay, that constant can be obtained by field theory. So, both all this can be done, this is called Ubogov-Korsin constant, okay, that is a constant. Okay. So, let me just sketch it, I am not going to do detailed derivation, but I will tell you how to renormalize kappa. An idea is exactly similar to what we did for hydro, not much difference. Okay. So, first let us do Rg of kappa. So, this is equal, I mean there is a force, but force is active at only large scale. We assume that force F theta is active at large scale and is not active at k in the intermediate range, well I mean intermediate range where I want to compute the renormalized kappa. So, this is gone, and what is that nonlinear term which was u dot grad theta, right. So, grad will give me k, the u is here and theta is here, convolution. So, q and p and q plus p is equal to k, straightforward. Okay. So, let us draw the Feynman diagram. Okay. I hope you will learn, I mean at least that part you will have courage to write the diagrams, and you should be able to calculate yourself. So, vortex will be k. Okay. If you do real calculation, there will be some tensor stuff and so on, but we just have this vortex is k, is a right now is a vector which does not look good, but I assure you that if I do it properly then I can get a vortex, okay, and I have velocity field u and theta of p and this velocity of q. Okay. So, I am going to work for theta given u. So, given velocity field, so u do not touch, I am not going to I assume that u is given to me and I am going to correct kappa by expanding theta. Okay. So, here idea is to expand theta by Green's function. Okay, this is g of p of theta. Now, what will it give me? So, this is u here. So, what would be the legs for coming out from this vortex? This vortex also will be p in fact, right. I mean there will be IP is ik. What would be come out of theta? So, if I expand Green's function, what will that be? So, this g inverse. So, theta of p is Green's function of p and this nonlinear term which will be integral, okay, and instead of p I write dr p dot u of r and theta of s, and what is r and s? R plus s equal to p, right. I mean I just have to rewrite it, but with change of variables. I should not write pq because that pq is already taken. These are dummy variables, r and s. So, I get r here. So, u will combine with u of q here and u of r here, u of r, and this will be theta of s. Okay. Now, what should be r in terms of q? R should be minus q, right, to get non-zero value. If r is minus q, then what is s here? What is s? P plus q, which is k. So, this is theta of k. So, this part of the diagram is going to give me correction to kappa, right, that is what we did before. So, this loop diagram, okay, this is whatever number I get, let us say integral I1, and this integral I will write this as delta kappa minus delta kappa k squared. Actually, this should be plus, I am sorry, this should be plus, right, that is plus. So, minus delta kappa k squared, and this I can take it to the left hand side. So, kappa plus delta kappa k squared. Okay. So, this is a correction to kappa. I skipped the step of course graining and so on, but that part you know already. I mean I am sure you are very used to that part. Okay. So, this is a correction from Feynman diagram, and if you do the algebra all of it properly, you can get a correction. And this for isotropic homogeneous turbulence, kappa of k also goes as k to power minus 4/3, like viscosity. There will be different coefficients, but that is the stuff. Okay. So, this for renormalizing kappa. What about energy flux for theta? flux computation. Okay. So, I can write down equation for the energy. So, d by d theta of k dt equal to, well, let us put here plus kappa k squared theta of k, and right hand side was k dot up theta of q, right, integral minus I dp like that, right. So, what do? I should multiply by theta star k standard both sides and add complex conjugate. So, I get d by dt of mod theta k squared. Okay. So, here I get dissipation which is 2 kappa k squared theta k squared, right. So, this is positive positive, so they get added up. In Schrodinger equation that went away because of I, because you have to be careful, and here minus I integral dp k dot up theta q theta star of k, okay, and add complex conjugate. So, you will find that this will be plus I, and I will get real part of that. So, I will get imaginary part of this. Okay. So, if you do the algebra right, I will get this. So, this is the term which is increasing energy. So, this T of k theta nonlinear transfer to k at Wave number k by theta theta interactions. So, what should be the flux, nonlinear flux for a sphere of radius k? I have T of k. So, by definition 0 to k T k prime T theta of k prime, right. That's the formula which I used very often. So, if I do the integral, I get minus dk prime dp, there is a dp sitting here, I am just going to substitute it here, k dot up theta q theta star of k. So, it is a 3 wave interaction. So, u of, let us put u of p theta of q, I am going to put a dash, theta is okay to put dash, and then theta star of k. U is given to me, u is, I do not do anything on u, but I am going to expand to 0th order, this will be 0. Okay. These are random fields, so they will give 0. I need to go to the first order, next order. So, I will get Green's function for, I am expanding theta k, okay, or let us say theta k. Okay. There is a star there, but do not worry about that part. There is a vortex here which I will ignore. So, what is going to come out of from the right hand side? When I expand theta, what will I get? 1 u and 1 theta, right. So, 1 u will combine with this u, up will combine with, from this side I will get u of minus p, and theta of q will combine with theta minus q, and there is a Green's function of k. Okay. Of course, k equal to, there is a complex conjugate, that is why k equal to p plus q, it all comes out. So, this integral involves integral c of p, which is velocity correlation function, and temperature or scalar correlation function q, and Green's function of k, and I got dp and dk. Okay. So, you do this complex integration and you will get the flux. For phi third regime, which is Kolmogorov regime, this will be a constant, which is epsilon theta. Okay. So, all this algebra will give you flux, and given this you can also derive a spectrum for temperature. I may have one free slide. So, I can write down the expression for theta, E theta of k. So, it turns out to be, if I did get it right, epsilon theta is linear in epsilon theta, epsilon u, which is dissipation rate of velocity field, minus 1/3, k minus 5/3, and k Ubokov Korsin, relation. This is a constant which is non-dimensional constant. Okay. So, this is a spectrum for E theta, and this number can be computed by field theory. Okay. So, and this. So, field theory tools can be applied to secondary fields. This is for scalar, but we can do it for MHD as well. MHD is more complicated. For convection, it is not very well done, I would say, but because it is anisotropic. Once you bring in anisotropy, field theory it gets more complicated. There are works on that, but it does get more complicated, but it can be done. And that is the problem, no? I mean, I think if you guys are interested in challenge, then apply to thermal convection. Okay, a good field theory is lacking in this. I did lot of work on turbulence, MHD turbulence. Okay, still there are lot to be done. So these are the areas which are not touched by they are hard problems.